Alright, today we're going to cover indexed sets and the well-ordering principle. At least what it is. We won't do any proofs with it, but considering this is the end of sets, I should introduce these things that haven't been introduced yet, because these are very important. So first of all, index sets. This is more like a way to write things in a little bit of a shorter fashion than having to write out a whole bunch of operations. For instance, our question here is, can we shorten the intersection of A1 with the intersection of A2 and A3 and A4 and A5, and this could have an infinite amount of sets? And the answer is, well, yes, of course we have notation for that. And for intersections, it looks like this. We do a big intersection sign, and we say this is the intersection from I equals 0 to n of a capital A with a subscript I. And what this means is if you have I starts at 0, this means you have A0 intersection A1 intersection A2, and this goes all the way up to AN. And similarly with unions, we do the same thing. The exact same notation, except instead of intersections, we have unions. And this will also go up to A sub n. You can start this index at whatever number you want, and you can end it at whatever number you want. You'll see this is exactly similar to when we have our sigmas of small numbers, which simply means A1 plus A2 plus all the way up to A sub n. This is a normal convention that we use in a lot of different sort of operators to shorten things up. So this is something that you should probably know. In fact, I am going to add one little thing here, is that the way these operations work, let's say we want to go to n plus 1 starting from 0. Well, this is the same thing as taking the intersection from 0 to n and of A sub I, and then using the intersection with A sub n plus 1. So these are equivalent operations, and in some proofs you may have to break things up like this. For instance, if you're doing anything with induction. In fact, to make this more clear, I should put brackets around this. But these are operations you can do and ways to shorten these huge sections of intersections or unions. Now with the well-ordering principle, this is something that comes up in proofs a lot and is used for proving the division algorithm, which I will show eventually when we get to the number theory portion of this series. In fact, in an elementary number theory course, this is one of the very first things you prove. And this well-ordering principle is an axiom, which means it has no proof, we just take it for granted. And basically what it says is that any non-empty subset of the natural numbers has a least element. So remember, the set of natural numbers is 1, 2, 3, all the way to infinity. So if we have some subset, and the subset has at least one number, which means, okay, that number might be 1, it might be 4, it might be 9, who knows. There's going to be a smallest element, which basically means the number that is chosen leftmost is the smallest element. This is kind of obvious because if you have a set, let's say A is the set, and we have some random numbers, I, j, and k, and we know that these are all in the natural number sets. Then the least element is going to be the smallest value out of the three. So if k is less than j, which is less than I, then k is the smallest element. And this well-ordering principle states that every non-empty subset of the natural numbers will have one. Now, if we extend this to the integers, there is a problem here. 1 is in the set of full integers, we can have negative infinity. So we can't say there's a smallest element since, well, there's an infinitely small element and we don't know what that is. However, if we were to say, okay, let's just do z plus, then We can also say yes, there is a least element in there too, because 0 is the most minimum possible element. So this is the well-ordering principle. This is an axiom we take for granted, and I know I didn't really prove it, but I gave some explanations as to why, and we don't even need those explanations. If there was no logical explanation for this, this would still hold because we've said it was a theorem. Obviously it wouldn't be a theorem or rather an axiom, if it didn't have some grounds in math, but that's what an axiom is. We take it for granted. Anyways, I know that was pretty short, but these are just some small things that I haven't covered that probably should have been covered, so I just made a video on that. I don't have any practice questions for this stuff, but I do have an interesting little exercise for you. If I were to take the intersection from I equals 0 to n plus m of ai, how would I break that up into something to something of ak? And I'm going to put this in brackets. With the intersection of j equals something to something of aj. And I want you to think for a second, and I'll come back with a nice little solution for you. Okay, so if we want to split up an intersection, our first number is going to start at 0, and we're going to go all the way up to n, or m, one of the two. And our second value, so I'll write this out, this is a 0 all the way up to a sub n, and now of course we should start here at a sub n plus 1 and go all the way up to a sub n plus m. So we start at n plus 1 and we go all the way up to n plus m. And that's a cool little thing with index sets that hopefully you should be able to see is fairly intuitive. If you have troubles with these proofs, just break them up into their corresponding components. And hopefully you'll be able to see what's going on. And if I did this with the union, it would be exactly the same, so I won't even write it out. But that was index sets. Hopefully you learned something. If you have any questions, as always, just leave them in the comments, and I will get to them as quickly as possible.